This is video help for problem 11.3. In a perfect world, we would take our data and we would take an inverse Fourier transform from that data to get our spin density. It would be real, have zero phase, and if we thought about a phase map, well, the phase map would be, the phase is just constant zero, and we would just have some constant color in our grayscale for all of y and x over a slice. Remember where S of k came from. We actually had a read gradient running along in time, and we set this up to have an echo with this, dephasing part in the beginning. Then we rephase it. We have an echo, and we set it up right in the center. And if you define our time with, go to t prime where it's 0 in the center, then that's where we'll have a maximum signal, and it echoed. And actually, the t prime really it really came in our phases with gamma bar g times t prime, and so that naturally brought forth the variable k. K is better because it also has the g in it, because we can change our k space or k value with g, not just with time. Now, here's what happens. Suppose the echo is not at the center by design or by error, but rather it was at k equal k0. In other words, our peak is not at k equals 0, t prime equals 0 corresponds to k equals 0. It's not at k equals 0, but instead it's at k equal k0, some non-zero value. Well, mathematically, what you know is that means that instead of this function s of k, what we're really looking at is the function s of k minus k0. So if we know that function, now we can find out what our inverse Fourier transform would give us. We think this is our spin density, but in fact, it's now not. It's changes. Remember, when we reconstruct in general, it's not quite the same as rho, and so we call that rho hat. And by the shift theorem and just redefining variables here, really, I can rewrite this as e to the plus I 2 pi k0x times the original integral up here, the original spin density. So my reconstructed inverse Fourier transform, reconstructed spin density, now has a phase in it. Not only does it have a non-zero phase, but the phase changes with x. The phase is 2 pi k0x. That k0 is that offset in k space. If I looked over a range, if I thought about x going over delta x, let's just say symmetrically from minus delta x over 2 to delta x over 2, then my phase, I just plug in, multiply 2 pi k0, my phase will go from minus pi k0 delta x, here's my phase, up to pi k0 delta x. If that delta x is big enough, this will run all the way from minus pi to pi. This will run over full 2 pi. And in that case, right at that a full range of phase, a 2 pi range, would correspond to a k0 equal 1 over delta x, or a delta x equal 1 over k0. And then, now when you look at your phase map, now, what you would have is, say, the most negative value is black, the most positive value is white, and you'd have a grayscale. You'd have something that was dark and then, middle and then light to white, black to white in your grayscale. And therefore, for every delta x that I'm referring to here, I will get a stripe. Why? Because although 2 pi k0x is different for all x, this e to the I 2 pi k0x is not. That's what's in our rho hat. When we're measuring this, we go backwards to get this phase, but the measurement, the intensity, the grayscale that we have as a function of phase will only be different over a 2 pi range. When I go to the next 2 pi, that phase, that e to the phase, just is repeated. Even though the phase changes, the e to the I phase changes, or e to the phase changes. And then I end up with repeats. Every delta x repeats. Those are the stripes. Now you can, just go back and recognize the relationship between k and t and get your shift. You see, if you have a k0, that corresponds to a new echo time, not 0. And we define that as delta t echo shift, or delta t ES.